Welcome to the A-level section of our YouTube channel. In this video, we want to explore electron affinity. By the end of this video, you will be able to understand electron affinity and its periodic trends. And that is, why is electron affinity, why does it increase from left to right across a period, and why does it decrease from top to bottom in the group? To begin with, let us define electron affinity. Electron affinity is simply the amount of energy released when an electron is added to a neutral gaseous atom or molecule to form a negative ion. In a more specific way, it is simply a tendency of an atom to attract electrons. Therefore, the stronger the attraction, the more energy is released. Let's look at a general illustration using chlorine. Chlorine here has got 17 protons, which means it has got 7 electrons in the outermost shell. So in order for this shell to be complete, it needs one more electron. So this electron can simply add onto the gaseous chlorine atom to form a chloride anion. So this electron, as it is being added to this outermost shell, which has got 7 electrons, there is energy that is going to be released. So that amount of energy that is going to be released when one electron is added to a gaseous chlorine atom to form a monovalent chloride anion is what we call electron affinity. Let's look at the first, second, and electron affinity. First electron affinity is the energy released when the first electron, so the first electron is added to an atom, leading to the formation of a monovalent anion. Now, what happens here, like we said, is when this electron is added, in the case of elements like oxygen that are in group 6, they have the ability to gain 2 electrons. So they'll first start by gaining the first electron to form a monovalent anion of oxygen. So when the first electron is added, we know that there is some energy that is released. And since energy is released to the surrounding, that one is going to be exothermic. Hence, when you check the value that has been given in this example is negative 144 kilojoules per mole, which is also agreeing that first electron affinity is actually exothermic. That's why it is carrying a negative charge. Now, this same anion here, monovalent anion that has been formed, we can still add one more because it only has 6 at the moment. So it now has 7. At first it has 6, now it has 7. So it needs one more. So we can still add another electron. So when we add another electron, then it is going to form a divalent anion. Now, what is going to happen is, as we are adding this electron, there will be a force of repulsion that will be experienced due to the presence of this electron that we already added. So that force of repulsion is going to cause an absorption of energy. So instead of the energy being released like it did in the first one, but here it's going to be an absorption of energy. And because of this, the energy that is associated with the second electron affinity is actually what? Positive. Therefore, it is endothermic. So this is what happens. So just to summarize this one, the nature of electron affinity, we are saying the first electron affinity is released, so meaning it's exothermic, which is negatively charged, so the energy is negative. The second one, due to the repulsion, it is endothermic, which will give us a positive value. Let's look at the periodic trends in electron affinity as we did from the introductory part of this video. So we said electron affinity increases across a period, that is from left to the right, and then it decreases as you go down the group. Okay, it decreases as you go down the group. So I think that is the periodic trends. Now, what we are interested in is what are the factors that affect this trend? What is responsible for these trends that we have just seen? So number one, we can talk about the atomic size. Okay, atomic size is responsible for the two trends that we have seen. Both across the period and down the group. The second factor that we're exploring in this video is the nuclear charge. This is also responsible. So let's have a look at how do these two things affect the periodic trends with regard to electron affinity. Let's look at atomic size. So we are saying atomic size, we are just talking about how the size of an atom becomes bigger. Now, this atomic size is determined by the number of protons that are available, because as you go down the group, you discover that the shells will be increasing because of the number of protons. So as the shells are increasing, it means the size is also what? Increasing. Okay, so now let's do an illustration with this example here. So this is a small, okay, this is a small size, and then this one is a big size. Now what happens here is that the basic structure of an atom, you realize that it has a nucleus. So in the nucleus, we find protons and electrons. So the protons are positively charged and the neutrons have got a zero charge, which means that the nucleus in general is positively charged because the only charge that is present in the nucleus is that of the proton, which is positive. Then in the shells, we have the electrons. Now the electrons, we know that they are negatively charged. So which means that opposite charges attract, as the general rule is. So which means that there is always an attraction between the electrons and the positively charged nucleus. So this attraction here, there is an electrostatic force of attraction that goes on here. Now, it follows that the shorter the distance, the stronger the electrostatic force of what? Of attraction. So when we look at the small elements, the distance here is short. So we have a short distance, meaning the attraction between the electron, the negatively charged electron, and the positively charged nucleus is stronger compared to when there is a bigger distance between the electron and the proton, as in this bigger atom here. So all what we are saying is the force of attraction here, the electrostatic static force of attraction here, it will be a little bit weaker. Here, it will be stronger because these are more closer. The electron and the nucleus are closer, but here the electron and the nucleus are a little bit further away. So the electrostatic force of attraction is going to be a bit weaker here. That is what we are saying. So just to conclude our point here, we are saying when you look at the distance from here to here, it is shorter. So we expect the electrostatic force of attraction to be stronger. As we go here, the distance is increasing, so the force is becoming weaker. Here, it is even more weaker. So it will continue being weak, and that is the reason why electron affinity also keeps what? Reducing. The same can be said about across a period. So across a period also you realize that the size of the atom also decreases as you move from left to the right. So atomic size can be used to explain both the decrease as you go down the group and the decrease as you go and the increase as you go across here, because here it is bigger and then here it is becoming smaller. So meaning the force of attraction here, the electrostatic force of attraction is becoming stronger and stronger, hence the increase in electron affinity. Now the decrease here is the opposite. We start from small size to bigger size. So the force is becoming weaker and weaker, hence the decrease in electron affinity. The other factor also that is important is the nuclear charge. So let's begin by first defining what nuclear charge is. So we are saying the nuclear charge is defined as the total number of charge in the nucleus due to the presence of what? Positive charged protons. So the number of protons as we move through the periodic table, the atomic number continuously increases due to the increase in the number of protons. So as you go from this side of the periodic table, we go to this side of the periodic table here, the number of protons increases. In fact, if you remember your IGCSE very well, we discovered that the way they had arranged the elements on the periodic table, it was according to the increasing atomic number. So as you move from left to right, the number of protons was increasing. So if the number of protons are increasing, meaning the positive charge is increasing, hence the nuclear charge is also increasing. So if the nuclear charge is increasing, meaning the electrons that are in the outermost shell will be tightly pulled. So the higher the nuclear charge, the more tightly the attraction of the electrons towards the nucleus would be. And this is the reason why the electron affinity will increase from left to right across the period in the periodic table. That is the explanation that we are interested in. Okay, now let's look at some periodic trends. So generally we are saying the electron affinity will increase from left to right, but there is this point we are saying here. We are saying although electron affinities generally become more negative from left to right across a period, there are several exceptions to this rule. Now let's look at boron here and let's look at carbon. These are actually in the same period. So boron, and then you go to carbon. Now, what you notice here is boron, you go to carbon, you notice that we are expecting, yes, it is expected that carbon is going to be having a higher electron affinity because it is on the right side of what? Of boron. Now, there is one point that you need to take note of, which confuses people mostly, is the fact that here, when we are talking about electron affinity, is the more negative the number is, the higher the electron affinity. So when we say this one is more negative, and then the one which is more positive has got less electron affinity. The one that has got more negative has got a higher electron affinity. So let's look at boron, for example, here. Boron is somewhere here, which can be a negative less than 100, but carbon is going to be negative above 100. So a negative that is above 100 is more negative. So this one is more negative. Therefore, it is going to be having a higher electron affinity. Let's look at the one which has got numbers here, and so that you know what we are talking about. Let's look at boron. I was talking about boron here. So boron has got negative 27, as you can see. Then carbon has got negative 122 kilojoules per mole. Okay, so now when you compare these two values, when you follow the number line system, negative 27 is bigger than negative 122. But as what we are saying is, since negative 122 is more negative than negative 27, it means that the boron here has got a higher affinity because it is more negative. So the more negative something is, the more negative the value is, the higher the electron affinity. That's what we are saying. So this brings me now to what we are calling the anomalies in the periodic table. So it is expected that as we move from the left to the right across the periodic table, we are going to experience an increase in electron affinity. But this isn't the case when we meet certain points. For example, I'll pick on carbon and nitrogen. Now, nitrogen is on the right side of carbon. So under normal circumstances, we expected nitrogen to be more negative, meaning a higher electron affinity. But this isn't the case. Carbon is more negative than nitrogen. Now, what we want to find out is the reason why. We should be able to explain these anomalies, and that is what we are going to explore in a short while. Then also look at oxygen here. Okay, so this oxygen here and nitrogen, we expect that nitrogen has got a less electron affinity than oxygen. Yes, it is expected, but it is something also that we're going to give a comment on. Nitrogen, why is nitrogen having a lesser, but yet when you compare using the electron configuration, it is going to give you something else. So we want to explain the anomalies here using electronic configuration. So let's explain using electronic configuration. So we are saying atoms with stable electronic configuration can make it challenging to add electrons. Therefore, they have more electron affinity. So if something is stable, meaning it has a higher electron affinity. Now, what is the stability that we are talking about here? So we are saying stability here, we are saying atoms which have got half filled. So you know we have got the S, the P, D, and so S, P, and D orbitals. Those are the ones that we deal with mostly, though we also have F. So we know that this one, it needs 2 electrons to be filled. This one, it needs 6 electrons to be fully filled. This one, it needs 10. So now, if we only have half, here we have 1, here we have 3, and then here we have 5. If something that has got half is more stable compared to something that is got a full one, That's what we are saying. So a stable configuration that we are looking at is the one that has got half of each. Now, why is it the case? Now, when you are filling in electrons, can we focus on here? Okay, when we are filling in electrons, let's look at the configuration for element X. So the configuration for element X, you discover that in the p orbital, there is this part here. Okay, there is this part which has got 2 electrons. So when the electrons are together like that, there is repulsion because they are both negatively charged. So this repulsion is what we call the spin pair repulsion. Now, this spin pair repulsion, it makes this element which has got this configuration to be unstable. But if we have an electronic configuration, which here, because this is the p orbital, so this is the px, so this is the px, this is the py, and this is the pz. So in here, we are supposed to have 2, 4, 6, but instead we have 1, 2, 3. So they are all half filled, meaning there is no repulsion here, there is no repulsion here, there is no repulsion here, meaning this one is actually highly what? Stable. That is the stability that we are talking about here. So the general idea that you should always look out for if you want to compare two things using electronic configuration is look out for the one which is more stable. The one which is more stable is expected to have what? To have a higher electron affinity compared to the one which is less stable. Please note that the example that I've used here, it's highly hypothetical. You don't have to go and look to say this one, the way it looks, I think it's oxygen or it's nitrogen. No, you'll be lost, but it's hypothetical. And the main point I was trying to emphasize here is on if the electrons are half filled, there is no repulsion, meaning it's stable. But if the subshells are filled, meaning there is spin pair repulsion, which makes it to be what? To be unstable. That's what I was saying here. So the more stable something is, the higher the electron affinity. And the stability is about how the subshells of the orbitals are filled up. So please take that into consideration. Now, let's look at this scenario here, why the electron affinity of nitrogen is lower than carbon, as we saw. Now, we expected that because carbon is on the other side, is on the right side of nitrogen, we expect it to be what? We expected it to be higher, but here is the opposite. So why the electron affinity of nitrogen is lower than carbon? So to understand this, let's examine their electronic configuration. So by now, I expect that we all know how to write the electronic configuration. So for example, carbon, which is C12 and 6. So we are using 6 to write electronic configuration. We are going to have 1s, 2, and then we are going to have 2s, 2, and then we're going to have 2p, 2. So this is what we're going to have. So when we add 2, 4, 6, we are going to have the 6 which is at the bottom here. So that is for carbon. So the electronic configuration will be written like this. So meaning for nitrogen is going to be 1s, 2, 2s2, and 2s3. So let's now examine this electronic configuration and give an answer to this one. Why nitrogen's electron affinity is lower than carbon. So now electron affinity is the energy that is released when an electron is added. So meaning we are supposed to add an electron here in this orbital, also here in this orbital. That's where we are adding an electron. But notice that when you are dealing with carbon, carbon only has it has an empty pz, okay, empty pz. So meaning the electron will be added where? Will be added here, okay. So the electron will be added there. So if the electron is added there, whatever anion we are going to have here is going to be stable because there is only one electron here, and the one electron which you've just added, which makes it to be what? To be very stable because they are all half filled. So there is no electron pair repulsion. So this one is stable. Okay, I'll write ST for stable. Just my own shortcut. Don't do it in the exam. Then for nitrogen, notice that it is already half filled. So the way it is already stable. But since we are talking about electron affinity, we'll be forced to add an electron in this subshell, which is already occupied. So once we add this electron here, we are going to cause spin pair repulsion. And once we have caused this spin pair repulsion here, it means we have destabilized the nitrogen. Therefore, the electron affinity that will be produced here will actually be lower. So that is the reason why the electron affinity for nitrogen is lower than that of what? Carbon. So in case you are going through the notes, can you change this electronegativity? It was just a typo, change it to electron affinity. So in conclusion, the more stable the electronic configuration, the higher the higher the electron affinity that is expected. Let's look at another unique case. Another unique case is that of nitrogen and oxygen. Now, when you look at nitrogen, we are saying nitrogen, why electron affinity of nitrogen is less than 4O. Now, under normal circumstances, let's examine the electronic configurations here. Electronic configuration of nitrogen, we know that, yes, we're going to add an electron in here, therefore we've destabilized. Then for nitrogen, it is already not stable. So when we add another repulsion in here, we have destabilized it even the more. So under normal circumstances, we might say that, we might be tempted to conclude that, in this case, because oxygen, when we add here, there will be more spin pair repulsion. So this one is going to give a lower electron affinity. But it is not true. Now, the reason for that is slightly different. So the reason for that, we are going to give credit to the what? To the nuclear charge. Okay, the nuclear charge. So when we are comparing nitrogen and oxygen, you realize that oxygen has got a higher nuclear charge. Okay, remember, as you move from left to right, the nuclear charge increases due to an increase in the number of what? Protons. So the higher nuclear charge is able to overcome this destabilization here. Therefore, the electron affinity that will be produced is what? Is slightly higher. So that is the difference here. Please take note. Here, you are not just going to rely on electronic configuration, but you are also going to consider the nuclear charge here. So this one is unstable, but due to the higher nuclear charge, it is strong enough to overcome this repulsion that is caused here. Hence, it is going to give us a higher electron affinity. I hope that one is clear. In conclusion, I would love to state the electron affinities for halogens. We are saying they have higher electron affinities, and this is due to their what? Small size. Okay, they have small size, therefore they have high effective nuclear charge and an almost full outer shell of what? Electrons. So when an electron is added to the halogens with a very high electron affinity, high energy is what? Is released. And this graph roughly shows how the electron affinities they vary. Okay. All right. Thank you so much. I hope the mystery behind electron affinity has been understood. Keep visiting the channel.